This is a recast of the 7,000-word piece, Few-Shot Learning, FSL, from Schneepat.com. This article discusses few-shot learning, a subfield of machine learning that addresses the problem of learning from limited data. It explains how few-shot learning enables models to learn from only a small number of labeled examples, and its potential applications in various domains. The article also introduces different approaches in few-shot learning, such as transfer learning, meta-learning, and metric-based methods. It highlights the strengths and limitations of each approach and discusses their relevance in real-world scenarios. Additionally, the article explores few-shot object detection and the challenges involved in this field. Let's listen in.
Today, we're diving into the world of few-shot learning, FSL, a subfield of machine learning that addresses the problem of learning from limited data. Traditional machine learning algorithms typically require large amounts of labeled examples to train accurate models, but in real-world scenarios, obtaining such datasets can be challenging and impractical.
That's where few-shot learning comes in. It aims to bridge this gap by enabling models to learn from only a small number of labeled examples. This is particularly useful in situations where acquiring new labeled data is time-consuming or expensive.
FSL algorithms leverage techniques such as transfer learning and meta-learning to effectively generalize from a few labeled examples to unseen data. They focus on learning the ability to learn, allowing models to quickly adapt to new tasks with minimal supervision.
And the applications of FSL are vast. It has found uses in various domains, including computer vision, natural language processing, and reinforcement learning. By reducing the reliance on vast amounts of labeled data, FSL has the potential to revolutionize machine learning and make it more accessible and applicable to real-world problems.
However, it's important to note that FSL is still a relatively new and active research area. There are several challenges and limitations that need to be addressed. We'll touch on those in a moment, but first, let's define few-shot learning.
Few-shot learning, or FSL for short, is a branch of machine learning that aims to address the challenge of learning new concepts with limited labeled data. Unlike traditional machine learning techniques that require a vast amount of labeled examples to achieve high performance, FSL algorithms thrive in scenarios where only a small number of labeled samples are available.
The goal of FSL is to leverage the knowledge learned from a large number of previously seen classes to quickly adapt and generalize to new classes given only a few examples. This is achieved through the utilization of meta-learning techniques, which focus on learning the underlying process of learning itself.
FSL algorithms typically consist of two stages, a meta-training phase and a meta-testing phase. During the meta-training phase, the model is trained on a variety of tasks with different sets of labels. This enables the model to establish a robust and generalized learning mechanism.
The meta-testing phase involves fine-tuning the model using a few labeled examples from a new class, allowing the model to quickly adapt and generalize its knowledge to the unseen class. In summary, FSL aims to bridge the gap between supervised learning and zero-shot learning by enabling machines to learn new concepts with limited labeled data.
Now let's talk about why FSL is important in the field of machine learning and artificial intelligence. In addition to its applications in computer vision, FSL possesses great significance in addressing the limitations of traditional supervised learning methods.
That's right. FSL algorithms have the potential to address the need for large amounts of labeled data to achieve high performance. By leveraging just a few labeled examples of a new class, FSL enables the model to generalize and recognize unseen classes accurately.
This ability to learn from limited labeled data makes FSL highly useful in scenarios where acquiring large amounts of labeled data is expensive, time-consuming, or simply not possible due to privacy constraints.
For example, in medical diagnosis, FSL can be immensely valuable as it allows the development of accurate classifiers even with limited labeled patient data.
And not only that, FSL can empower machines to learn and adapt quickly in dynamic environments where the distribution of data is subject to frequent changes. This can be incredibly useful in real-world applications where things are constantly evolving.
Absolutely. By incorporating FSL techniques into machine learning and artificial intelligence frameworks, we can improve the ability of AI systems to learn and generalize efficiently from limited data, thus expanding their real-world applications.
Now let's briefly discuss the background and techniques in few-shot learning. Traditional machine learning algorithms require a vast number of labeled examples to accurately learn and generalize from the training data.
However, in real-world scenarios, obtaining such a large labeled dataset often proves to be challenging, expensive, and time-consuming. This is where FSL comes to the rescue.
FSL techniques can be broadly classified into two categories: metric-based and optimization-based approaches. Metric-based methods measure the similarity between instances using distance metrics and classify new samples accordingly.
On the other hand, optimization-based methods utilize optimization algorithms to adjust the model's parameters to represent and recognize new classes. Both approaches have shown promising results in addressing the challenges posed by the scarcity of labeled data.
That's correct. By exploring these future directions, we can expand the capabilities of few-shot learning models and open up new avenues for applications in various fields beyond just image recognition. This could lead to advancements in NLP, speech processing, and other domains where limited labeled data is a challenge.
Another approach to improving few-shot learning models is through the utilization of metric learning techniques. Metric learning focuses on learning a function that maps samples into a metric space where similar samples are closer together and dissimilar samples are farther apart.
By incorporating metric learning into few-shot learning models, they can learn a more effective feature representation that captures the underlying similarities and differences among samples. This can help the models better generalize from the few labeled examples available during training to unseen classes during test time.
One popular metric learning technique for few-shot learning is prototype-based learning. This involves learning a set of prototype vectors to represent each class. These prototypes capture the essence of the class and can be used for classifying new samples.
Other metric learning techniques, such as Siamese networks and triplet networks, have also been explored for few-shot learning. These techniques aim to learn a distance metric that preserves the relative similarities and differences among samples, further enhancing the model's ability to generalize to unseen classes.
Extending few-shot learning to different domains and tasks is also an important area of research. While it has been primarily applied to image recognition tasks, there is growing interest in applying few-shot learning to natural language processing, NLP, video recognition, and speech processing.
Absolutely. These domains often suffer from limited annotated data, and few-shot learning can provide an effective solution to learn from limited labeled examples. Techniques such as meta-learning, transfer learning, and generative models can be explored to enable effective few-shot learning in these different domains.
However, researchers and practitioners must also be aware of the ethical considerations and potential biases that may arise in few-shot learning models.
That's right. As FSL models are trained on limited data, there is a risk of perpetuating biases present in the training set, leading to biased decision-making. It's crucial to prioritize fairness, transparency, and accountability in the development and deployment of FSL models.
Additionally, the collection and use of data for few-shot learning must be done responsibly and ethically. Proper consent must be obtained from individuals whose data is being collected, privacy and data protection must be ensured, and the data must be sourced from diverse and representative populations.
Failure to adhere to these ethical principles could result in privacy breaches and further marginalization of vulnerable groups. So it's essential to approach few-shot learning with caution and consider the potential biases and ethical implications.
In conclusion, few-shot learning has emerged as a promising approach to overcome the limitations of traditional supervised learning algorithms in scenarios with limited labeled data.
By leveraging pre-existing knowledge and transferring it to new tasks, few-shot learning enables machines to quickly learn from a small number of examples.
The various methods and techniques discussed in the article, such as metric learning, generative modeling, and meta-learning, have all shown significant improvements in few-shot learning performance.
However, there are still challenges that need to be addressed, including scalability to large-scale datasets, standardized evaluation metrics, and the extension of few-shot learning to handle more complex tasks.
But the future prospects of few-shot learning are promising. It has the potential to revolutionize the field of machine learning and artificial intelligence by enabling machines to learn and adapt to new tasks with minimal labeled data.
Absolutely. The implications of few-shot learning are far-reaching, from computer vision and natural language processing to medical imaging and recommendation systems.
As research in few-shot learning continues to advance, we can expect more effective algorithms and techniques to be developed, unlocking the full potential of this approach.
And with responsible and ethical deployment, Few-shot learning can lead to improved system performance and enhanced user experiences across a wide range of domains. Understanding a background and techniques in FESL provides a solid foundation for further exploration of this rapidly evolving domain.
Absolutely. One of the main challenges of traditional machine learning models is the requirement of a large amount of labeled training data. These models rely on supervised learning techniques, which means they need a substantial dataset to train accurately. However, in many real-world scenarios, obtaining such a dataset can be extremely difficult and time-consuming.
Yes, that's especially true in fields like medical diagnosis, where gathering labeled data for rare diseases or complex conditions can be challenging due to their low incidence or the need for expert annotations. This limitation restricts the ability of traditional models to perform well in scenarios where only a few labeled samples are available.
Exactly. That's where transfer learning comes into play. Transfer learning is a popular approach that involves utilizing knowledge and learned representations from one domain or task to improve performance in another related domain or task.
In the context of few-shot learning, FSL, transfer learning is essential in overcoming the limited availability of labeled data. By leveraging knowledge from a large-scale dataset or a pre-trained model, FSL models can transfer their learned knowledge to the few-shot learning scenario where only a few labeled samples are available for each novel class.
This allows FSL models to infer meaningful representations and generalize well to new classes with minimal supervision. Transfer learning can also be applied in FSL to adapt models trained on a source domain to perform well on a target domain, even when the data distributions between the two domains are different.
That's right. This enables the FSL model to learn domain invariant features that can be robustly applied to novel classes in various domains. Overall, transfer learning plays a pivotal role in improving the performance and generalization abilities of FSL models by allowing them to leverage information from related domains or tasks.
Another powerful technique in FSL is meta-learning, also known as learning to learn. Meta-learning focuses on leveraging prior knowledge to adapt quickly to new tasks with limited labeled data.
Meta-learning algorithms typically consist of two main components, a meta-learner and a task-specific learner. The meta-learner learns from a distribution of tasks by updating its parameters based on the performance of the task-specific learners. This allows the meta-learner to capture underlying patterns and generalize them across different tasks.
In the context of FSL, meta-learning has shown promising results. By learning how to learn, meta-learning algorithms can effectively utilize the few available labeled examples during training to achieve better generalization on unseen tasks.
That's right. The meta-learner can rapidly adapt to new tasks by adjusting its parameters based on a few labeled examples, thus alleviating the requirement of a large labeled dataset. Additionally, meta-learning can help in mitigating the issue of catastrophic forgetting by retaining knowledge from previously encountered tasks and applying it to new ones.
Absolutely. Few-shot classification methods have been actively researched in recent years to address the challenges of learning from limited labeled examples.
One prominent approach is meta-learning, which involves two stages: pre-training and fine-tuning. In the pre-training stage, a large-scale dataset is used to train the meta-model on various classification tasks. Then in the fine-tuning stage, the model is fine-tuned on a specific few-shot classification task. This two-stage process allows the model to acquire knowledge from pre-training tasks and transfer it to unseen tasks during fine-tuning.
Another popular approach is metric-based learning, which learns an embedding space where similar instances are grouped closer together. This framework allows for classifying novel instances by comparing their distances to labeled instances in the embedding space using distance metrics like Euclidean distance or cosine similarity.
And let's not forget generative models, such as variational autoencoders or generative adversarial networks. These models have also been utilized for few-shot classification by generating synthetic examples to augment the limited labeled data.
Absolutely. These few-shot classification methods have shown promising results in addressing the challenges of learning from limited labeled examples. They provide effective frameworks to tackle the scarcity of labeled data and facilitate rapid adaptation to new tasks.
Understanding and exploring these techniques is crucial in the field of few-shot learning, as they provide innovative solutions for real-world scenarios where labeled data may be scarce or difficult to obtain.
That's right. One approach mentioned in the article is the prototype-based method. This method relies on the concept of prototypes, which are representative examples of each class. During the training phase, prototypes are learned from a set of labeled samples.
The prototypical network is an example of a prototype-based method. It operates by learning a metric space in which samples belonging to the same class are closer together than those from different classes. This metric space enables efficient classification of new samples based on their similarity to each class prototype.
Prototype-based methods have shown promising results in few-shot learning tasks because they leverage the idea of using prototypes as a compact representation of each class. They provide a flexible framework for solving few-shot learning problems.
That's right. Prototype-based methods can also be extended to incorporate additional information such as class relationships or other forms of side information, making them even more powerful in solving few-shot learning problems.
Moving on, another approach mentioned in the article is the exemplar-based approach. This approach is based on the idea that humans learn to recognize new categories by comparing them to previously seen examples.
In the exemplar-based approach, a set of support examples from the few-shot categories is used to train a model. During testing, the model is presented with a few query examples from the same categories and has to classify them based on the similarities with the support examples.
The exemplar-based approach is advantageous because it avoids the need to explicitly learn a separate representation for each category. Instead, the model can leverage the diversity of the support set to generalize well to novel examples.
Additionally, the exemplar-based approach can handle fine-grained and subtle differences between classes, as the model can learn to discriminate between similar examples within a category. However, a potential limitation of this approach lies in its reliance on a large support set, which can be challenging to obtain in real-world scenarios.
That's an important point to consider. Lastly, the article introduces metric-based methods as another powerful approach to tackle few-shot learning.
Metric-based methods learn an embedding space where similar instances are grouped closer together, while dissimilar instances are pushed further apart. This is achieved by training a metric function that computes the distance or similarity between instances.
One popular metric-based method mentioned in the article is prototypical networks. These networks define a prototype for each class in the embedding space. During inference, a query instance is assigned to the class whose prototype it is closest to.
Another metric-based approach mentioned is relation networks. These networks learn to compare a pair of instances and output a similarity score. By comparing a query instance with each support instance in a few-shot task, relation networks can determine which class the query instance belongs to.
Metric-based methods have shown impressive performance in few-shot learning tasks, outperforming traditional approaches by a large margin. However, they often require a substantial amount of annotated data for the support and query sets during training, making them less suitable for realistic few-shot scenarios.
That's a trade-off to consider. While metric-based methods show great potential, they do require more labeled examples during training compared to other approaches.
Absolutely. It's important to understand the strengths and limitations of each approach in few-shot learning and choose the most suitable one based on the specific requirements of the problem at hand.
Well said.
One popular approach mentioned in the article is the use of Siamese networks for similarity learning. Siamese networks are designed to compare and measure the similarity between two input samples. They consist of two identical subnetworks that share the same weights and parameters. Each subnetwork takes one of the input samples and maps it to a lower dimensional feature space. The outputs from both subnetworks are compared using a distance metric, such as Euclidean distance or cosine similarity, to determine the similarity between the two samples. This similarity score can be used to classify new unseen samples by comparing them with the labeled examples in the training set. Siamese networks have shown promising results in few-shot learning tasks, where they can effectively learn a discriminative similarity metric and generalize well to unseen classes with only a few examples.
That's right. Another approach mentioned in the article is relation networks. Relation networks leverage deep neural networks to model the relationship between examples in a few-shot learning setting. They also use a Siamese network architecture, where two deep neural networks share the same weights and encode the input examples into feature representations. These representations are then used to compute a similarity score between pairs of examples, which is used to classify the query examples. Relation networks excel at comparing and relating examples within a few-shot learning context, allowing them to generalize well and adapt to new classes with limited labeled training data. They have shown impressive results across multiple benchmark datasets, outperforming several state-of-the-art few-shot learning approaches.
Optimization-based methods have also been utilized in few-shot learning to optimize the parameters of the model for better generalization to new classes. One approach mentioned is the prototypical network. This network learns a metric space where each class prototype is the mean of its support instances. During inference, a query instance is mapped to the metric space and classified based on its proximity to the class prototypes. This method has shown promising results in various few-shot learning tasks.
Another optimization-based approach is model-agnostic meta-learning, MAML. MAML aims to learn an initialization of the model parameters that can be quickly adapted to new tasks with few samples. It achieves this by updating the initial parameterization using gradient descent on a set of tasks. MAML has been successful in few-shot learning tasks across different domains and leverages the principle of learning to learn. The model is trained to quickly adapt to new tasks by updating its parameters based on a few samples. Optimization-based methods like MAML have been proven effective in few-shot learning scenarios and are currently an active area of research.
Absolutely. Optimization-based meta-learning, also known as MAML, is a powerful approach within the field of few-shot learning. It aims to learn a good initialization of model parameters that can quickly adapt to new tasks with limited examples. The key idea behind MAML is to optimize the model parameters in a way that enables rapid task adaptation through a few gradient updates. This is achieved by computing high-level gradients with respect to the whole training set and performing individual gradient updates to approximate the adaptation process. By explicitly modeling the task-specific adaptation during training, optimization-based meta-learning has demonstrated significant success in addressing the challenge of few-shot learning.
That's right. Optimization-based meta-learning has been applied to various domains, including image classification, object detection, and reinforcement learning, and has shown improved generalization capabilities compared to traditional deep learning methods. It provides a promising avenue for enhancing the performance of models in few-shot learning scenarios and holds great potential for future research and practical applications.
Absolutely. Understanding these different approaches allows researchers and practitioners to choose the most suitable method for their specific few-shot learning problem. Siamese networks, relation networks, and optimization-based methods like MAML all have their strengths and limitations, but they each offer promising ways to tackle the challenges of few-shot learning.
That's right. One popular approach in few-shot learning is model-agnostic meta-learning, or MAML. MAML aims to learn an initialization of a model that can be quickly adapted to new tasks with only a few examples. It achieves this by training the model on a variety of tasks, each with a small number of examples. During this training phase, MAML learns to update the model's parameters in a way that allows for efficient adaptation to new tasks.
MAML has shown promising results in few-shot classification tasks, such as image recognition and object detection. One advantage of MAML is its flexibility. It does not make assumptions about the underlying task distribution, making it applicable to a wide range of few-shot learning scenarios. Additionally, MAML is model agnostic, meaning it can be combined with any type of model architecture, such as convolutional neural networks or recurrent neural networks.
However, there is a drawback to using MAML. It requires a large amount of computational resources to train due to the iterative process of task adaptation. This can be time-consuming and costly. Despite this limitation, MAML has demonstrated remarkable performance in few-shot learning tasks, making it an important technique in the field.
Moving on to few-shot object detection, which is a fundamental and challenging task in computer vision. Traditional object detection methods rely heavily on large-scale labeled datasets for training their models. This makes them unsuitable for scenarios with limited labeled data.
That's where few-shot object detection comes in. It aims to address the limitations of traditional object detection methods by enabling the model to learn from a smaller number of annotated examples. One popular approach is based on meta-learning techniques, which involve meta-learner networks trained to adapt rapidly to new classes using a few labeled examples.
These few-shot object detection algorithms show promise in scenarios where acquiring a large labeled dataset is challenging or expensive. However, there are still significant challenges to overcome. One challenge is handling the inherent domain shift between the base and novel classes. Another challenge is improving the model's ability to generalize to unseen class configurations.
Ongoing research in this field is focused on developing more robust and practical few-shot object detection systems. Researchers have explored the concept of meta-detectors, which leverage meta-learning techniques to enable fast adaptation to new object categories with limited training data.
One example of a meta-detector is the meta-RCNN framework. It adopts a two-stage detection architecture and uses a meta-feature generator to extract discriminative features from base categories. These features are then used to initialize a meta-model, which is fine-tuned on few-shot target categories using a meta-learning algorithm.
Another approach is proto-meta, which introduces a prototype-based meta-learning mechanism. It employs a meta-learner network to generate prototypes for each object category. These prototypes are used to compute the similarity between the query image and the prototypes during inference, achieving competitive few-shot detection performance.
Both meta-RCNN and proto-meta demonstrate the potential of meta-detectors for addressing the challenges in few-shot object detection. They provide a promising direction for future research in this field.
Understanding these different approaches and techniques is crucial for advancing the field of few-shot learning and improving the performance and generalization ability of few-shot object detection systems.
Absolutely. These approaches aim to combine few-shot learning with object detection, which has gained a lot of momentum in recent years. The challenge is to recognize novel classes with limited labeled examples while accurately localizing the objects of interest in an image.
One common approach is to use pre-trained models on large-scale datasets to extract visual features that capture the necessary information for both classification and localization tasks. These features are then used as inputs for a few-shot learning algorithm, which learns and generalizes to unseen instances using a few labeled examples from the novel classes.
Additionally, object detection frameworks like faster RCNN and YOLO have been modified to incorporate few-shot learning techniques into their architectures. This integration allows these models not only to recognize novel objects, but also to accurately bound them within an image.
The combination of few-shot learning and object detection provides a promising avenue for addressing the challenges of recognizing and localizing new objects with limited training data. However, there is still room for improvement, especially in terms of scalability and robustness in real-world scenarios.
That's right. Now let's talk about the applications and challenges in few-shot learning. One significant application is in healthcare, where few-shot learning can be used to diagnose rare diseases. With limited data available for such diseases, few-shot learning algorithms can leverage small labeled datasets to accurately identify and classify these conditions.
Few-shot learning also finds utility in computer vision tasks such as object detection and segmentation. By enabling models to learn from a few examples, it has the potential to improve the performance of these tasks in scenarios where obtaining large labeled datasets is challenging or expensive.
And in the field of natural language processing, few-shot learning algorithms can be employed for tasks like semantic parsing and sentiment analysis. These applications benefit from the ability of few-shot learning algorithms to generalize knowledge from a few labeled examples.
However, few-shot learning faces several challenges. One significant challenge is the lack of diverse and well-annotated few-shot datasets, which restricts the generalization capabilities of few-shot learning models. Without diverse datasets, the models may struggle to perform well in real-world applications.
Additionally, the training of few-shot learning models requires careful consideration of the meta-learning techniques used to parameterize and update these models. This introduces its own set of challenges that need to be addressed.
Future research in addressing these challenges will contribute towards the widespread adoption and advancements in few-shot learning technologies. Now let's move on to the real-world applications of few-shot learning.
Absolutely. Real-world applications of few-shot learning are expanding rapidly, with various fields benefiting from its capabilities. One such field is computer vision, where few-shot learning has proven to be highly effective.
By utilizing a limited amount of labeled data, few-shot learning algorithms can be trained to recognize novel objects or classes. This is particularly useful in industrial automation, autonomous driving, and surveillance systems. For example, few-shot learning can enable autonomous vehicles to quickly understand and respond to new traffic signs, pedestrians, or road obstacles.
In the medical field, few-shot learning can be utilized to assist in diagnosis by recognizing rare diseases or conditions based on a few annotated examples. This can be game-changing for patient care, especially in cases where large annotated datasets are not readily available.
Furthermore, few-shot learning has demonstrated its value in natural language processing. By leveraging a small number of labeled examples, few-shot learning algorithms can be utilized in machine translation, semantic understanding, and sentiment analysis tasks.
With the ability to rapidly learn and generalize from limited data, few-shot learning holds immense potential in revolutionizing various real-world applications across a range of disciplines.
However, it's important to note the challenges and limitations in few-shot learning as well. One of the main challenges is the scarcity of labeled data. Traditional machine learning models rely heavily on large sets of labeled data, but few-shot learning requires the ability to generalize from only a few examples.
This scarcity of labeled data poses a significant challenge in deploying few-shot learning in real-world scenarios where the availability of labeled examples is limited. Additionally, domain shift presents another limitation in few-shot learning. The difference between the distribution of data in the few-shot training phase and the actual deployment phase can negatively impact the performance of few-shot learning models.
And let's not forget about class imbalance. In few-shot scenarios, there is typically an unequal distribution of samples across different classes, making it difficult to effectively learn the features of minority classes.
These challenges and limitations highlight the need for further research and development to enhance the effectiveness and applicability of few-shot learning approaches. There is still much room for improvement in this field.
Absolutely. Understanding these challenges and limitations will help researchers and practitioners improve upon existing techniques and develop new ones to overcome these obstacles.
One area for future research is the development of few-shot learning models that can effectively handle multi-label classification tasks. Currently, most FSL methods focus on single-label classification, but in real-world scenarios, there are often multiple labels associated with an object or image.
That's right. Being able to handle multi-label classification would be a significant step forward in the field of few-shot learning. It would allow FSL models to better handle complex real-world scenarios where objects or images can have multiple attributes or categories.
Another interesting direction for future research is the dynamic adaptation of classes based on available data. This means that instead of training FSL models on predefined classes, the classes can be dynamically selected based on the data at hand.
Yes, this interactive and flexible approach could involve reinforcement learning techniques to select the most relevant and informative samples for training. By adapting the classes dynamically, FSL models can better capture the nuances and variations present in the data and improve their performance.
And it's not just about image recognition tasks. There is a need to extend the scope of few-shot learning to other domains such as natural language processing, NLP, or audio analysis.